Hello, everyone. My name is Sebastian Brandt. I'm a postdoc at ETH Zurich, and this is joint work with Alkida Balliou, Fabian Kuhn, and Dennis Olivetti from University of Freiburg. In this talk, I would like to show you new lower bounds for the maximum independent set problem, and more generally for a class of problems called bounded degree or bounded out degree dominating sets, which contains the MIS problem. And we would like to study these problems on trees in the standard local model of distributed computation. Let me start with the definition of a maximally independent set. A maximally independent set, or MIS, is a subset of the nodes of the input graph that satisfies two properties. The independence property, which tells us that each node that is in the MIS is not allowed to have any neighbors that are also in the MIS, and the domination property, which tells us that any node that is not in the MIS must have a neighbor, so a node within distance 1 that is in the MIS. MIS is a very useful subroutine for many algorithms for other problems in the local model. And as such, we would like to really understand it very well. But it might also be the case that if we use maximum independent set as a subroutine, we do not need the full power of maximum independent set. Maybe some relaxation of maximum independent set might already suffice. And as such, we are also very interested in understanding relaxations of maximum independent set. One natural way to relax the MIS problem is to relax the domination property by not requiring that each non-MIS node has a neighbor that is in the MIS, but instead requiring that each such node has a node at least within distance, at most beta, that is in the MIS, where beta is just some parameter of the problem. And this is actually a very well-studied problem called the beta ruling set problem, which has not only been studied from the upper bound side, but since last year also from the lower bound perspective. The second natural way to relax the MIS problem is to relax the independence property. So we do not require that each MIS node has 0 MIS neighbors, but we allow up to k neighbors that are in the MIS. And we call this problem k degree dominating set. And this will be the focus of today's talk. In fact, the lower bounds that I will show you today also apply to a further relaxation of this k degree dominating set called k out degree dominating set. But to keep things simple, we will focus on k degree dominating set. On the technical side, we require that this parameter k is at most delta to the epsilon, where delta is the maximum degree of the graph, and epsilon is some parameter that is at most 1. Great, so let me tell you what is known about the complexity of computing such a k degree dominating set. And on the deterministic side, regarding upper bounds, what is known due to the recent breakthrough result by Rozon and Ghaffari on network decompositions and the follow-up work by Ghaffari, Kuhn, and Rozon is that we can compute k degree dominating sets both for k equals 0 and for larger k in polylogarithmic time in the number of nodes of the input graph. On the lower bound side, we have, due to two different works, log n divided by log n lower bounds for MIS and larger k. But if you look at these lower bounds closely, what we will see is that the lower bound instances, so the worst case instances in those lower bounds, are actually line graphs. In particular, these lower bounds do not hold on trees. And on trees, we really have nothing better than this omega of log star n lower bound that goes back to lineal from 87 if k is at least 1. If k is 0, so for the MIS problem, there's actually a much larger lower bound, root log n divided by log n lower bound from last year. So there we know that the correct answer also on trees is in the polylogarithmic regime. On the upper bound side, if we restrict to trees, we do not only have polylog n upper bounds, but actually we know since 2008 that we have log n divided by log n upper bounds. Our new lower bounds are omega of root log n lower bounds that hold for all these k. So we know that even if k is at least 1 or larger, we get that the correct answer for k degree dominating set must lie in the polylogarithmic regime. So we get a large improvement for k at least 1 and at least a very slight improvement, but well, great simplification in the proof of the lower bound for MIS on trees. On the randomized side, our lower bounds get exponentially worse. So we only have root log n lower bounds, while the upper bounds unfortunately do not get exponentially better. We have well, root log n upper bounds due to Ghaffari from 2016. So there's still an exponential gap between lower and upper bounds in the randomized case. So before I tell you a bit more about how we achieve those lower bounds, let me say a few words about the model of computation, which is just the standard local of distributed computation introduced by Lineal in 1987. So in this model, the nodes of the input graph are computational entities that communicate via the edges. Communication and local computation of the nodes proceeds in synchronous rounds, where we do not limit the message size or the local computation in any way. And the runtime of the distributed algorithm will just be the number of rounds until the last node terminates. And if you're not very familiar with the workings of the local model and the details, that is not a problem for today's talk. So it's possible to follow this talk without knowing basically any more specifics about the local model than I told you now. All right, so let's have a look at the techniques that we use. And one of the main techniques is the round elimination technique, which goes back to the round elimination theorem proved 2 years ago that states that for any locally checkable problem, we can, in some automatic fashion, find another locally checkable problem that can be solved precisely one round faster. And here, locally checkable just means that the problem can be described via local constraints, which holds for all the problems that I've shown you so far. There is some technical fine print for the applicability of this theorem, but nothing that cannot be dealt with by using known techniques, so nothing we have to worry about. How do we use this theorem to actually learn something about the complexity T0 of some problem pi0 that is given to us, for instance, the MIS problem? Well, what we can do is we just apply this function R that this theorem guarantees us that returns a new problem pi1 that again is locally checkable and has a complexity that is precisely one round less than the complexity of pi0. And then we apply this function again to pi1 and so on, generating a sequence of problems with the property that each subsequent problem has a complexity of precisely one round less than the complexity of the previous problem, given that the previous problem was not yet solvable in 0 rounds. And if we get to a problem with index, say, k, that can be solved in 0 rounds, then we know that the original problem pi0 must have a complexity of precisely k. Now, if we cannot find such a problem that can be solved in 0 rounds, but we know that after k steps, we haven't reached such a 0-round solvable problem yet, then we know that the complexity of pi0 must be at least k plus 1. So we can still use it as a lower bound technique. Unfortunately, there is an issue when trying to apply this technique to some problem pi0. Namely, for most problems pi0 one starts with, what happens is that the size, the complexity of the descriptions of the problems grows very fast. So already after a few steps in this process, one usually reaches a problem that is so complex to describe that one cannot feasibly understand it, much less determine whether it can be solved in 0 rounds or not. Standard way to remedy this problem is to just start with one of these automatic round elimination steps, and then to insert a relaxation step, by which I mean that we transform the obtained problem pi1 into a new problem pi1 prime that has a complexity that is at most as large as the complexity of pi1, but also is much smaller in description again. In this automatic step, we lose precisely one round of complexity. In this relaxation step, we lose an unknown amount of rounds, but at least 0. And now that our problem is small and understandable again, we can again apply one of these round elimination steps, which might grow the description of the problem, and then insert a relaxation step again, and so on. And these problems that we get on the diagonal, well, they will have the property that any subsequent problem has a complexity of at least one round less than the complexity of the previous problem. So again, if we just look for the first 0-round solvable problem on this diagonal, then the number of steps it took us to get there will be a lower bound for the complexity of the initial problem pi0 that we are actually interested in. Now, to get a good lower bound, what we would like is that these relaxation steps that we execute are tight or close to tight. Because if we lose a lot of rounds of complexity in these steps, then the amount of steps that we take before we reach the first 0-round solvable problem might actually be much smaller than the true complexity of pi0. So really the big open problem to make this technique work well, and in general to find lower bounds in the local model, is to find a good way to relax problems. Now, to summarize and maybe present this from a slightly different perspective, what we want to do is we want to turn this automatic sequence that we can generate from the given problem pi0 into a relaxed sequence that we can actually understand, and for which the length of the relaxed sequence is not much smaller than the length of the automatic sequence. Ideally, the length of both sequences, where length just means the number of steps until we get to the first zero-round solvable problem, should be asymptotically the same. At least that is what we would like. Now, in this picture, it looks like all of these problems in the relaxed sequence have roughly the same size of description. This is not necessarily what happens, or at least what is known for the problems in the literature for which round elimination has been applied successfully. So let me try to give you a quick overview of the growth patterns that we can actually get in the automatic and the relaxed sequence, where we measure the complexity of the description of a problem just by the number of labels that are used to describe the problem. So if we are very lucky, then what will happen is that the automatic sequence does not exhibit any growth. And then we don't have to do anything in the relaxed sequence, and we will just, in some automatic fashion, get an omega of log n lower bound, which was the case, for instance, for problems like Lovász local lemma or delta coloring. But usually we are not that lucky. And then what happens, at least in all the cases that we have seen so far, is that we get a power tower growth in the automatic sequence. So in each step of the sequence, the number of labels grows exponentially or even doubly exponentially. Now, there are three ways known to deal with this. And the first one is to just embrace this growth, this power tower growth, also in the relaxed sequence, but somehow to make sure that the problems, despite the huge number of labels that are needed to describe the problems, are still, in some sense, understandable. And this, well, works for some problems, but only yields lower bounds that are log star n or log star delta for problems such as 3-coloring a ring or weak coloring. But if one wants to get good lower bounds, or let's say larger lower bounds, then one would like to have much smaller growth in the relaxed sequence. So ideally, what we would like is to have no growth at all in the relaxed sequence. And actually, there are lower bounds for maximum matching, and as a consequence, also for MIS, where this happens, where one can find suitable relaxations such that the relaxed sequence does not have any growth at all, and this results in an omega of log n divided by log n lower bound. Another scenario is that we are not able to get the growth of the relaxed sequence down to no growth at all, but we can at least reduce it to polynomial. And there is a lower bound of this kind, or lower bounds for ruling set, that also applies to MIS on trees, which is the lower bound of root log n divided by log n, and is proved in this work that I already mentioned before. Now, it's not necessarily the case in general that if one has no growth at all in the relaxed sequence, that the lower bound that one achieves will be better than if one has polynomial growth. But if one looks at this specific lower bound, at least for ruling sets and MIS on trees, then the fact that the lower bound is not better than root log n divided by log n partially comes from the fact that the growth is still polynomial. So if one could get this polynomial growth down to no growth at all, one would have good hope that one would get a better lower bound. So a natural question to ask here, is this polynomial growth here actually required? And at this point of time, well, it might not be really well defined what I mean by that it is required. So let me try to explain this. And for that, let's take a quick look at these relaxations. So in these relaxation steps, what we have to guarantee is that the complexity of pi1 prime is at most as large as the complexity of pi1. And the only way we know how to guarantee this is to show that if we are given any solution for pi1, we can transform it without any communication, so in 0 rounds in the local model, into a correct solution for pi1 prime. Now, if we restrict to these kinds of relaxations, it is well defined to ask, is it possible to get, say, no growth at all in the relaxed sequence for, say, the problem of MIS on trees if we want to get at least a lower bound of, say, larger asymptotically than root log n divided by log n. What we said in this paper that proved this root log n divided by log n lower bound is that we do not believe that such a polynomial, that such a relaxed sequence that has no growth at all actually exists, just based on some calculations we ran. But in fact, it turns out that if we allow some cheating, one can actually get a relaxed sequence that has no growth at all. And here the cheating consists in considering graphs with certain inputs. Now, considering graphs with inputs usually sounds like a bad idea if one wants to prove lower bounds, because, well, restricting attention to smaller graph class just can make the lower bound smaller. But in fact, considering this framework, it might actually help in this step where we want to prove that we can transform any solution for a problem pi1 into a solution for pi1 prime. And to give an example for how this could help, let's just assume this problem pi1 is the perfect matching problem. And this problem pi1 prime, for which we want to show that we can actually zero-round transform any solution for perfect matching into this solution for pi1 prime, is the singles orientation problem, which is the problem of orienting the edges of a graph such that no node is a sink. So each node has at least one outgoing edge. And for simplicity, we will assume that the graphs that we consider are 3 regular graphs. Now, asking whether there exists such a zero-round transformation, it is not hard to show that if we are given some solution for perfect matching, we cannot zero-round transform it into a solution for singles orientation in general. But if, say, we restrict our graph class to graphs that are bipartite and where each node knows in which part of the bipartition it lies, then it suddenly becomes zero-round transformable just by doing the following. For each edge that is in the perfect matching, we orient the edge from purple to orange, and each edge that is not in the perfect matching is oriented from orange to purple. And that ensures trivially that each node has at least one outgoing edge. So what we can take away from this is that inputs can help in this step, in this relaxation step in this framework. And as such, they can also help to prove lower bounds. Specifically for our problem of interest, the k-degree dominating set problem, what we use to get the lower bounds is a delta edge coloring. So we only consider graphs that are delta regular that come with a delta edge coloring as input. And using this delta edge coloring suitably to find good relaxations, we actually achieve these omega of root log n deterministic and omega of root log n randomized lower bounds. Now, this is basically all I have. Let me maybe conclude with an open question, an open problem. And this is just the general question of figuring out what other inputs than delta edge coloring we can use for which other problems to actually find better relaxations and prove better lower bounds than what is the state of the art. That is all I have. Thanks for your attention. I hope you enjoyed the video, and I'm looking forward to seeing you at PODCI.